Hi everyone, my name is Carlos Enrique Coronado and I am here to present you the poster of my research work titled Metallographic, Structural and Mechanical Characterization of Welded Plates of an Austenitic Iron 31 Manganesum 8 Aluminum 1.9 Carbon Low Density Steel. Actually, I am doing my postdoctorate in the Department of Mechanical Metallurgy in the Institute of Research in Metallurgy and Materials in la Universidad Michoacana de San Nicolás de Hidalgo, Mexico. Abstract. The automotive industry has made significant efforts in weight reduction of steel components to improve fuel efficiency and reduce carbon dioxide emissions. Recently, low-density steels have gained importance due to their lower density, corrosion resistant, and high mechanical strength with high elongation. However, its welding implies challenge due to their fast transformation. Second, fast precipitation, hot cracking, chemical segregation, and embrittlement. This research work examines microstructural changes in heat-affected zones during the GTAW process of an austenitic Iron 31 Manganesum 8 Aluminum 1.9 Low-density steel and their impact on mechanical behavior. Characterization techniques include light optical microscopy, scanning electron microscopy, X-ray diffractions, Vickers microhardness, and micro-tensile tests. Results showed a dendritic structure and non-metallic inclusions in fusion zone, equiaxial and deformed grains, and 𝜅-carbides in both halves. Tensile tests revealed the lowest yield strength and ultimate tensile strength in fusion zone and the highest values in has 2. The lowest elongation was found in has 1. The microhardness peak values were found near to the fracture. Introduction. Iron, magnesium, aluminum, and carbon steel is a high-strength, lightweight alloy known for its exceptional tensile strength, good ductility, and corrosion resistance. This is achieved through solid solution strengthening and precipitation hardening. Its typical composition includes 5 to 30% magnesium, 1 to 10% aluminum, and 0.3 to 2% carbon, leading to 4 types of microstructure: austenitic, ferritic, austenitic-based duplex, and ferritic-based duplex. Aluminum reduces the density of steel, while magnesium and carbon enhance mechanical properties. Research work has shown that welding changes the microstructure and mechanical properties as tensile strength and tautness, affecting the has with precipitation particles of second phases. Aluminum promotes the formation of 𝜅-carbides in the austenite matrix, precipitation hardening, and enhancing strength and ductility, although their effectiveness depends on their distribution and morphology. The challenge in developing the low-density steels involves the precise processing required to ensure uniform 𝜅-carbide distribution within the austenite matrix. Experimental procedure. In the Table 1, chemical composition of the LD steel used is shown. Iron balance, magnesium 31%, aluminum 8%, carbon 1 to 1.9%, nitrogen 0.050%, phosphorus 0.01%, and sulfur 0.001%. In the figure 1, a microstructural conditioning of LD steels by heat and thermomechanical treatment is shown. In the figure 2, autogenous GTAW process parameters. B. Schematic design of micro-tensile sample in millimeters, and C. Schematic design of double B bevel joint is shown. Results. Figure 3. Engineering and true stress strain curves and mechanical properties. Subsection A. Fusion zone. Subsection B. has 1 and subsection C has 2. In the figure 3 illustrates the engineering and true stress and strain curves for the studied zones. Different behaviors were observed in each zone due to the varying heat input conditions. Generally, the results showed the fusion zone exhibit the lowest yield strain and ultimate tensile strength because of its dendritic structure, which also corresponds to the lower hardness observed. Added to this, the maximum elongation was reached in HAS2. Conversely, the comparison between HAS2 and HAS1 and HAS2 reveals very similar yield strain and ultimate tensile strength values in the welded joint. The maximum yield strain and ultimate tensile strength values were exhibited in HAS2, followed by HAS1, with slightly lower values, thus a marked tendency is shown here. This similarity is attributed to the lack of significant changes in their microstructure with the precipitation of 𝜅-carbides and equiaxial grains in both zones. The difference in tensile properties of the HAS may be due to the activation of the microband deformation mechanism in HAS2, where those microbands are narrow regions of plastic deformation that form within the crystalline structure of the material during deformation. The increase in the mechanical strength of steel is typically associated with a decrease in deformation capacity. However, the steel in the figure 4 shows the micrographs of the specimen deformed up to fracture. These micrographs reveal the microstructure near to the fracture shown. It is evident that a deformed grains were produced in the adjacent zone to the fracture, presenting elongated grains due to the applied load. This small zone exhibits elongated grains aligned in the direction of stress. In the fusion zone, the presence of a dendritic structure results in significantly more dendritic elongation during plastic deformation. Notably, fusion zone elongation exceeds HAS1 and HAS2 due to the higher mechanical strength of the last two zones. Figure 5. Same micrographs of the fracture surface, subsection A, fusion zone, subsection B, HAS1, and subsection C, HAS2. In general, the fracture mechanism in the different samples of low-density steel was generated by ductile fracture type. The impulse in the fracture surface and the low presence of flat zones can be observed. The main characteristic of the ductile fracture type is a nucleation and growth of dimples that may show coalescence. Typically, these dimples form due to the presence of precipitated particles, but after a tensile test, these particles create voids that become visible and can be of different sizes according to the particle logic. This type of morphology helps ductile behavior and increases the percentage of elongation reached. Taking as a reference the elongation data in figure 3, figure 5 shows a higher reduction area in the fusion zone, which is consistent with a higher elongation in comparison with HAS1 and HAS2. It is observed that the fracture surface is not completely uniform, since there are regions of brittle behavior as well as defects due to the welding process. It was observed two areas, Zone 1 and Zone 2. Zone 1 was predominant and was characterized by its irregular shape, with pronounced relief concentrated around the impulse that showed coalescence between them. This behavior is associated with a higher degree of ductility in the alloy. Zone 2 is characterized by flat surfaces. The reliefs in this zone are thinner, and there is also smaller numbers of dimples on the fracture surface due to the dendritic structure generated. On the other hand, figure 5 subsection C, corresponding to HAS2, a zone with a higher concentration of 𝜅-carbides, but there are more flat areas with sharper peaks. As a result, this zone exhibits the lowest elongation percentage but the highest strength. Figure 6. Vickers microhardness profiles along the plastically deformed zone by micro-tensile test. Subsection A, fusion zone, subsection B, HAS1, and subsection C, HAS2. Figure 6 shows the Vickers micro-hardness profiles performed on the plastically deformed zone of the micro-tensile specimens of low-density steels. These profiles provide critical information on the variation of mechanical strength across the regions comprising the welding joint. From the figures, it is evident that there is a higher hardness in the zone near to the diffraction occurs, indicating significant hardening due to the localized plastic deformation during the micro-tensile test. Another important point is the consistency observed among profiles from different samples, suggesting that the conditions were practically identical due to the applied stress in the zone, which increased dislocation density and consequently the hardness of the fracture, regardless of the specific region studied. Once the peak hardness value near to the diffraction zone is reached, a reduction in hardness was observed as a distance increase. This is because the plastic deformation is concentrated in a small area known as necking, where the most significant strain hardening occurs. Beyond this area, the grain size and other conditions remain consistent with those observed in post-welding conditions. Furthermore, it is understandable that Has2 exhibits the highest values due to the 𝜅-carbide precipitation. Figure 6, subsection D, X-ray diffraction patterns. In the Figure 6, subsection D presents the diffractograms obtained from the samples deformed by the micro-hardness test. The presence of austenitic phase is evident, indicating that it remains the predominant phase under various processing conditions, including hot rolling, solutioning, and welding. The diffractogram displays the dominant peaks of iron in the planes 111 and the iron in the planes 200. Additionally, a small single peak is visible on the left side of the second main austenite peak, identified as K200 carbide in the fusion zone. For heat-affected zone 1 and heat-affected zone 2, no evidence of K-carbide is observed. There are variations in the height of each peak, which may correlate with the phase volume fraction in the study area. However, the diffraction intensity of each phase also largely depends on the orientation of the grain in each phase. Conclusions. Conclusion 1. The stress-strain analysis shows that the fusion zone has the lowest yield strain and ultimate tensile strain due to its dendritic structure, while Has1 has the highest ultimate tensile strain because of K-carbides that enhance its hardness and tensile properties. Conclusions 2. Metallographic characterization identifies a dendritic structure in the fusion zone, while both heat-affected zones 1 and 2 show equiaxial and deformed grains with K-carbides. Conclusion 3. Fractographic analysis indicates that low-density steel fracture mainly in a ductile fracture type, with the fusion zone showing the highest elongation, whereas Has1 and Has2 exhibit a mix of ductile and brittle fracture. Conclusion 4. Micro-hardness profiles show a significant hardening near to the fracture zone, especially in Has2, with hardening decreasing further from the fracture. Conclusion 5. X-ray diffraction analysis reveals that the austenitic phase is dominant across all processing conditions. A small peak for the K phase was observed in the fusion zone, but its low concentration made it difficult to detect in other conditions.